stop. Garrett here. Oh, come on, Seth. We're going on an adventure.
I don't even know who you are.
Okay, Seth, now that we're here.
Well, how did we even get here?
Okay, keep up the questions, and I'm putting you in the back. Come on, Seth, we have to grab something for the back.
What are we grabbing?
Just come here. Have to grab something for the object. Doesn't matter.
Bro, I haven't been
What the?
fed in weeks. Can you please give me something, man? Please, bro, no, don't leave me. Bro, come on. No,
I got it.
man, please.
Why is there a person in your trunk?
No questions. Hey, Ewan, do you want to make some quick money really fast?
Sure, thanks.
Okay, hold on to this first. Now, what I want you to do is I want you to, with your right hand, just spin it 360 degrees, just right like that, and if it lands with this pink dot still up, then you get $10. Ready? Give it a try. Better luck next time.
Can I solve the money?
Hey, Pablo, do you want to do a trick for us?
Yeah, sure.
See this pink dot on top?
Yep.
Keep it on top, and you're going to flip it, and if the pink dot's still on top, you win.
Okay.
Okay?
What? Whoa! Whoa!
Hey, Alisher, do you want to make some quick money fast?
Yeah.
Quick
sure.
$10, okay? Pink dot still on top, you get $10. Sound easy?
Yeah, easy.
Okay.
Well, how?
Eigenvectors. Next person.
Where are we? You're on.
Oh, shoot. Hi, I'm reporter Garrett Miller-Junk. I'm here with
who?
Seth Chin. Oh, they're the first person. Come on. You want to make some money really fast, really easily?
Sure, man.
Okay, you start with it like that. You're gonna toss it up, make it rotate 360 degrees. Again, pink dot still on top. If you're able to do that, $10 is yours. Go. Better luck next time.
So why exactly are we doing this, man?
Because we need marks.
Okay, could you please explain to me how on earth this thing works?
Say no more. Concept review. So how does this whole thing work? Why is it the object moves in this manner? Well, in order to understand this, we're going to have to go into conservation of energy, conservation of momentum, projectile motion, and a few other physics concepts. To begin with, as soon as the object leaves our hand, it's going to be a projectile, meaning the only forces acting upon it would be gravity and air resistance. This means that as soon as the object leaves our hand, it's going to be modeled only by gravity, showing that the rotational motion will be the same as if it's in an enclosed system. On to you, Seth. Now look over there.
Where? Oh, so now the second part to realize is that all objects spin around their center of mass, and this means that the rotation can be modeled as if the center of mass was the entire object. This means that the object can be modeled as a singular point, and now that we understand that, all we need to do is look at the motion of the object.
Oh wait, I can see what you're doing. I'll take it from here. As we can see, this object is undergoing rotation, circular motion about its center of mass. Since its object is undergoing constant rotation, we can see that torque, the force that causes this motion, is seen here. Through measuring torque during the rotation, we can see that there is a correlation between torque itself and rotational velocity as well. Since we are dealing with three-dimensional movement, we can express any instantaneous rotation being underwent on this object by a point in this three-dimensional space represented by a vector about the origin.
How do you get out of my car? Anyways, now that we have a way of visualizing this, we can look at two key insights during the rotation of the object. If we take the non-inertial reference frame of gravity, it can appear that the velocity of the object is constant, and it appears as if the Earth is instead accelerating towards it as the object maintains a fixed position at the center of mass. By doing this, the apparent velocity of each point of the object will not change due to a gravitational acceleration. On to you, Seth.
So now that we no longer have to deal with gravity, we know that the rotational momentum of the object is conserved, because momentum is always conserved. This means that if we calculated the starting rotational momentum of the object, we could calculate other velocities that would lead to that rotational momentum. Since the rotational momentum is correlated to torque, we can express this on the three-dimensional torque space we already established. When we plot all of these points, we see that mass is not always symmetrical in every axis, meaning we see what looks like an ovoid.
Now another part of this is that we know energy is always conserved. And since we are no longer considering gravity, we know that the kinetic rotational energy will remain constant. Since this energy relies on rotational velocities, it can be modeled using the three-dimensional torque space.
However, since this model uses velocity squared, it is a bit more spherical. However, it is still a three-dimensional ovoid. When both of these objects are charted, we can see that they intersect in two circles. This represents velocities that the object can move between in order to remain stable in its motion.
Notice while the object is three-dimensional, it only has two circles that show the stability of its motion, meaning that only two of its axes of motion are stable, meaning if we rotate it along the third axis, this motion becomes unstable, leading to the strange pattern of strange motion that we've observed.
This would have prevented the person from catching the object in its original position after 360 degrees of rotation about that axis. This is because the object would have also spun about the other axes in such a way that it would have also appeared to have rotated 180 degrees in the smallest axis.
Yeah, you got it, Seth. Now there's one thing I have to tell you. You need to wake up!